Alright, so in this video, we'll be looking at finding the concentrations of ions in solution. So this is something that is pretty simple, and I think it'll make a lot more sense just going through an example than trying to explain it. So let's just start with an example. Let's say that we have a solution of sodium chloride, a NaCl solution that is 0.5 molar. So we have a solution that has a concentration of 0.5 molar. So these square brackets, in case you didn't know, are just used to denote concentration. So this just means the concentration of the NaCl solution is 0.5 molar. All right, so we have this solution, and we need to find the concentration, again, square bracket, the concentration of the sodium ions, these Na plus ions in this solution. So how do we do this? Well, sodium chloride is an ionic compound, and you should know that compounds like this, like NaCl, in solution will actually dissociate into its constituent elements, in terms of ions, rather. So this will actually dissociate into Na plus and Cl minus. That is, for every one NaCl molecule, we'll get one Na plus, or one sodium ion, and one chloride ion. And so, based on this, for a 0.5 molar solution of NaCl, we can say that we'll have a concentration, or we'll have a sodium ion concentration of 0.5 molar as well. So, if this isn't too clear, we can set it up stoichiometrically, and I'm sure it'll make a lot more sense if it isn't doing so already. So we can say that we have 0.5 moles of NaCl per liter, right? So this moles per liter notation is just the same thing. It's equivalent to molar. So again, like I said in the the molarity video, this big M is really almost just shorthand for moles per liter. These two are equivalent, moles per liter. So this 0.5 moles per liter, 0.5 moles of NaCl per liter, and based on our expression, this dissociation expression that we have here, we know that for every 1 mole of NaCl, we will get 1 mole of Na plus ions, right, of sodium ions. So by canceling out moles of NaCl, we can see that we'll have 0.5 moles of Na plus per liter. Again, this is equivalent. This is the same thing as what we had over here. Alright, so I hope this is making some sense. We can look at another example to further clear things up. Okay, let's say we have a different solution this time, right? Let's say we have a magnesium chloride solution, right? A magnesium chloride solution, MgCl2, that has a concentration of 0.1 molar. So we have a 0.1 molar MgCl2 solution. So what do we want to find? Let's try to find these three things. One, let's find the concentration of magnesium ions. Two, let's find that concentration of chloride ions. And three, let's find the total ion concentration. So let's try to find these three things. Okay, well, let's just start first by writing out that dissociation expression. So we know MgCl2, magnesium chloride, is an ionic compound that will dissociate into its ions, right? Into Mg plus, let's write 2 plus, into, 1 magnesium ion and 2 chloride ions, right? For this MgCl2, we will get 2 chloride ions. So here, this is our expression for this dissociation. We really don't need to keep this 1 here, but I'm just, putting it there for clarity purposes. But, I thought let's put a 1 here too. So, well, we can write it out stoichiometrically, but really, if you can, remember to what we saw last time, well, we just had 0.1 molar. And we see that for every 1 MgCl2 molecule, we'll get 1 Mg2 plus. So, well, this should just be 0.1 times 1, giving us an answer of 0.1 molar Mg2 plus. But again, just for the sake of clarity, I can write it out stoichiometrically for this problem. But again, like you can see, it is very simple in that you don't, there's not a lot going on here, as long as you know this dissociation expression. So, writing out stoichiometrically, we see we have, again, 0.1 moles of MgCl2 per liter. Remember, we know what this means. This is just the same thing as our concentration in molarity. And we see that for every 1 mole of MgCl2, we get 1 mole of magnesium ions, letting us note that we actually get 0.1 moles of Mg2 plus per liter. That is what we got over here. Okay, so we got the first question, or the first part of this question, the thing that we were trying to find. That's a G. So let's just write it over here, right? We got our Mg2 plus concentration to be 0.1 molar. All right, let's do the next thing, right? Cl2. Let's try to find our not Cl2, our chloride ion concentration, right? So that's 0.1 molar, and we just see, again, looking at this dissociation expression, that it is just 2, right? So 0.1 times 2, so 0.2 molar Cl minus. For the sake, again, of setting it up stoichiometrically, let's just say 0.1 moles of MgCl2 per liter. And this time it's actually 2 moles of chloride ions. We're going to get 2 moles of chloride ions per every 1 mole of magnesium chloride. So that's 0.1 times 2, giving us 0.2 moles of chloride ions per liter. Exactly what we got right here. Okay, now let's move on to the last part. We were trying to find the total ion concentration. The total ion concentration. Well, before we do that, let's just write our, chloride ion concentration right here before we forget. All right, well, now we're trying to find the total ion concentration. So what does that mean? Well, I mean, the name really sums it up, right? It is the concentration of ions, of all ions in the solution. Well, we have our magnesium chloride solution, a 0.1 molar magnesium chloride solution, and we see that for every 1 mole of magnesium chloride, we will get 2 types of ions, right? 1 magnesium chloride ion and 2 chloride ions, meaning that for every 1, molecule of magnesium chloride, of MgCl2 that dissociates, we will actually get a total of 3 ions in solution, right? 3 ions in solution. So, well, that really can mean that we can write at our, let's see, this kind of glitching. Okay. So, we can say that 0.1 moles times 3 is 0.3 molar ions. Again, setting it up stoichiometrically. This is the last time I'm going to do it in the video, but 0.1 moles of MgCl2 per liter. For every 1 mole of MgCl2, we actually get a total of 3 ions, right? Or 3 moles of ions. So we get our answer of 3 moles of ions per liter. And that is exactly what we got here. Over here. Yeah. So that brings us into this problem. So I hope that makes sense, this idea of total ion concentration. So really, the only real way to mess this up, again, as you can see, it is pretty, simple, is just to mess up that dissociation expression. So just make sure that you guys know, your chemical formula as well. You know the charges of all the ion species, which you can just find by referencing the periodic table. There's a few you would need to memorize, but that aren't really necessarily you can find on the table. That's more so with, certain transition metals and things like that. But And also just make sure you know your polyatomics. That's another very important thing, and something that can cause you to make a mistake. So speaking of polyatomics, let's just look at one more example before we move on to a more exam style question. So let's say that we have another solution, and this time we have a calcium phosphate solution. That is a calcium phosphate solution, so PO4 2, that has a concentration of 0.2 molar. So now what are we trying to do? Let's do the same thing we did last time. Let us find the concentration of each of the ions that make up the compound and the total ion concentration. All right, we always start by writing out that dissociation expression, which in this case, again, this is why you need to know your your charges of everything, or your polyatomics. To be familiar with your polyatomics, we can say that this will give us 3 calcium ions and 2 phosphate ions. All right, so again, if you feel more comfortable doing it stoichiometrically, feel free to do so, but I will just be writing it out more in the shorthand style. So we have 0.2 molar solution, and we see that for every mole of our calcium phosphate, we will get 3 moles of calcium ions. So here, actually, let me do this just to, we can say our concentration of calcium ions is 0.2 molar times 3, or 0.6 molar. Okay, now for phosphate, our concentration of phosphate ions, well, again, the solution's concentration is the same, 0.2 molar, and we see that we get 2 moles of phosphate ions for every 1 mole of calcium phosphate that dissociates. So that's 2, giving us an answer of 0.4 molar. And finally, what is the total ion concentration? Well, the concentration of ions in this solution, 0.2 molar times, well, that's just 3 plus 2. For every calcium phosphate molecule that dissociates, we'll get 3 calcium ions, 2 phosphate ions, for a total of 5 ions. So that's 0.2 times 5, and that will just be 1 molar. And that is the answer. Or that's how you do this. So hopefully this is making sense. And let's just look at one last question. This is kind of going to be, a multiple choice style problem that you will likely see on an exam. So let's just say that we have, four different solutions. Let's say our first we have a potassium cyanide solution that has a concentration of 0.1 molar. Let's say, secondly, we have a aluminum sulfate solution, right? That is Al2SO4. So aluminum sulfate that has a concentration of 0. Let's just say 0.2 molar. Let's say now we have that a third solution. Let's just say this is NaCl, right? NaCl that is going to be 0.4 molar. And finally, we have a glucose solution, a solution of glucose that is C6. C6H12O6. And this is going to have a 0.15 molar concentration. So now we have these four different solutions with differing concentrations, and so what we have to find in this problem is which one of these 4 solutions has the highest total ion concentration. So take a minute to do this. I will assume that you did that, and you pause the video, and I'll just go through each of the options now. Well, let's start with the first one, potassium cyanide. We know potassium cyanide, again, this is why it's important to know your polyatomics, will dissociate into K plus potassium ion and a cyanide ion. That is a total of 2 ions, right? One potassium and one cyanide ion. So that is 2 ions this is going to dissociate into. So what we'll have to do is just take 0.1, the concentration of the solution, times the number of ions that it dissociates into, say 0.2 molar. Okay, next we have aluminum sulfate. Well, aluminum sulfate is going to dissociate into 2 aluminum ions, right? And 3 sulfate ions. So that is 2 plus 3, or 5 ions in total. So that's going to be 0.2 times 5, or 1 molar. Okay, now NaCl. We already looked at this NaCl before, right? We know NaCl is going to dissociate into an Na plus and a Cl minus. That is 2 ions. So that's just going to be 0.4 times 2, or 0.8 molar. And finally, we're looking at our glucose. This is actually a bit of a trick. You can see all of these, these elements that make up, and in rather large quantities, that make up just one molecule of glucose. But really, this is actually not an ionic compound, meaning it will not actually dissociate into ions, really, right? So this glucose is really just going to stay in this form in solution. It's not going to break up into ions like these others do. So really, what we're going to have is just 0.15 times 1. You're just going to have, for every 1 glucose, you're going to have that 1 glucose in solution still. So this is 0.15 molar. So again, be aware of your molecular compounds, your ionic compounds, be able to, know how to identify these, and you should be fine. Well, now obviously just comparing these 4 numbers, we can clearly see that 1 molar is the largest, and so our answer will be aluminum sulfate. So that brings us to the end of this video. I hope, it all made sense. This isn't something that is, crazy difficult compared to some other things that you may, see later in chemistry, but just make sure you keep your, charges, your formulas, and everything straight, and you should be fine. So, if you found this helpful, please show your support, subscribe, like, leave a comment of what you'd like to see next. I hope this was helpful, and I'll see you guys in the next video. Thank you.